What we are going to take up in this particular lesson is solubility. So to begin with, let's understand what is solubility. Solubility is defined as the maximum amount of a substance dissolved in a given amount of solvent at a particular temperature. So solubility is defined as the maximum amount of a substance that can be dissolved in a given amount of a solvent at a particular temperature. And this solubility is found to depend on several factors, like it depends on the nature of the solute and solvent. Number one, it depends on um, the nature of the solute and the solvent. Here I will give you the golden rule. The golden rule is like dissolves like. Okay, like dissolves like means what? If you have a polar solute, it will be soluble in a polar solvent, right? So a polar solute will be soluble in a polar solvent. For example, NaCl in water. NaCl has polarity, charge separation. Even water has polarity and charge separation. And if you have a non-polar solute, it will be soluble in a non-polar solvent. Okay, so non-polar solute dissolves in a non-polar solvent. For example, if you take naphthalene, naphthalene is an organic compound and it has no charge separation. So naphthalene is found to be soluble in benzene, because benzene is also a liquid, it's a solid but of no polarity. There also there is no charge separation. So what is the rule of solubility? Like dissolves like. The second thing on which the solubility will depend is the temperature. And the third thing, or the third factor, is the pressure. The solubility of a substance in a particular solvent depends on the nature of the solute in the solvent and the temperature and the pressure. So we are going to look at all these points now, and we will be taking up the first example as the first case as solubility of a solid in a liquid. So the first case that we are looking at is solubility of a solid in a liquid. Okay, so here you can just imagine example of like salt or sugar dissolved in water. Okay, so you take a solute, let's say you take some solid and you add it to a liquid. The two will be dissolved to give you a solution. The solution in the beginning is an unsaturated solution. Okay, unsaturated means it can dissolve more. Okay, it can dissolve more. So the solution is unsaturated, it can dissolve more. So you kept on adding more and more of the solute, the solid, to the solution, and it was, let's say, dissolving. A time will come when this solution will finally get saturated. Okay, so you have the solute which was added to your liquid solvent, and that was giving you the solution. And now the solution is saturated. The solution is saturated, and that means no more solute, no more solute can be dissolved at the given temperature. If you keep the temperature constant, then now no more solute can be dissolved in it. This solution is now saturated. Okay. And what happens is, when the solution is saturated, there is an equilibrium. There is an equilibrium which is established between the left side and the right side, which means the solute and the solvent will mix together to form the solution. What is this process known as? This process is known as dissolution. And at the same time, from the solution, the solute will be separating out. So the reverse process will also be happening here. And that process is called as crystallization. So there are these two processes going on hand in hand at equal rate. And what do we call this situation as? We call this situation as dynamic equilibrium. So dynamic equilibrium means that there are two processes going on, forward and backward. Which are these two processes here? Dissolution and crystallization. And the two processes are taking place exactly at the same speed, same rate. Now when it is so, okay, when it is so, what about the solution's concentration? When there are two processes going on, but the two processes are the opposite of each other, taking place at exactly the same rate, the solution's concentration remains constant. It remains constant. There will be no change. And this concentration, this constant concentration, okay, is the solubility. This constant concentration is defined as the solubility, because you remember the solution was saturated, and saturated means the maximum amount has been dissolved. No more can be dissolved. And how we define solubility? We define solubility as the maximum amount of the solute present in given amount of a solvent. So in a saturated solution, the amount of the solute is actually maximum. So remember, the concentration of a saturated solution is the same as its solubility. Okay. And now what we are going to look at is the effect of temperature and pressure on the solubility of this system. So number one, A, if I talk about the effect of pressure. Okay, the effect of pressure on the solubility. So you know what? There is no effect. There is no effect of pressure. There is no effect of pressure on solubility of a solid in a liquid. So this particular case only we are specifying that there will be no effect of pressure. And you know why? Because solids and liquids are almost incompressible. They can't be compressed. So there is no effect of pressure on the solubility of a solid in a liquid. Why? Because solids and liquids are almost incompressible. So no effect. And now let's look at the second factor. And what is that second factor? Temperature. Is temperature going to affect the solubility? Will it be able to increase it or decrease it? Now to understand this, we will have to look at two cases. Now what are these two cases? Number one, when the delta H solution, what is this? This is the enthalpy of solution, the energy change taken place when the solution was formed. So if the enthalpy of solution is positive, okay, it is positive, then such a process is what? Endothermic. And what are endothermic processes? Endothermic processes are the ones in which heat is absorbed. These processes absorb heat, so they are favored when they get more heat. So if the delta H solution is positive or the process is endothermic, then what happens? With increase in temperature, right, solubility increases. So with increase in temperature, solubility also increases. Only when the process of dissolution was endothermic, in which heat was absorbed. Now let's look at the second situation. When the enthalpy of solution, delta H solution, is negative, and negative means the process is exothermic. And exothermic means what? That in this process, heat is released. So this is a process in which heat is already being released. So this process is not in need of heat. It is already giving out heat, and such processes, as per the Le-Chatelier's principle, are favorable at a low temperature because heat is already being given out in this process. So these are not favored at high temperature. So if this is the case, with increase in temperature, what do you think will happen? With increase in temperature, solubility decreases. Solubility will decrease. So you just can't give an answer without knowing if the enthalpy of solution is endothermic or exothermic. Depending on the case, solubility may increase or it may decrease. So remember, endothermic processes are always favored at a high temperature and exothermic processes are favored at a low temperature. This is as per the Le-Chatelier's principle. We will now take up the second system, which is solubility of a gas in a liquid. Right? You must be aware that several gases are soluble in liquids. For example, oxygen gas is soluble in water, okay, and CO2 and even HCl, hydrogen chloride gas, they are also soluble in water. So these are just few examples, that oxygen, carbon dioxide and even hydrogen chloride gas, these are soluble in water. And we are now going to talk about this system and the effect of temperature and pressure on the solubility of such systems. Right. So to understand this, let's consider a case where in a container there is some liquid or a solvent taken. There is some solvent. You can take this solvent as water maintained at a particular temperature. Okay. And there is a gas above this solvent in the container. Right. So I've taken a gas above a solvent like water. What will happen with time? That the gas particles will start entering in. They will start entering in the solvent. So what we can say is that the gas starts to dissolve. After some time, the gas particles from the solution will again start going up in the gaseous state. So the two processes will be here going on are: one, the gas is getting dissolved, and two, from the solution the gas is again going back to the gaseous state. So what do you have now here is not just the solvent, but what is this formed finally? This is now a solution where a gas is dissolved in a solvent and the system is at dynamic equilibrium. Okay, what is dynamic equilibrium? When there are two processes going on hand in hand exactly at the same rate, but the direction is opposite. So you see here the gas is getting dissolved and it's going out in the gaseous state at the same time. So this system is in dynamic equilibrium. Two processes going on exactly at the same rate. Okay, now we make some change here. And what is that change? We are going to increase the pressure. We are going to increase the pressure on this system. So the system was earlier like, something like this. This was the level of the solution and the solution had the gas particles dissolved in it. So this is the solution. We are still keeping the temperature constant, but what we have done is we have increased the pressure. So when you increase the pressure from top, okay, when you are increasing the pressure from top, the particles in the gaseous state are compressed, right? The particles which were earlier in this much volume, now these particles have been confined to a smaller volume because you have applied pressure from top and the system has been compressed. So what we see here is now that the number of particles per unit volume increases. I am talking about the gaseous phase. The gaseous phase is only this portion above the solution. Okay, so the number of particles per unit volume now has increased. You can see the difference. Earlier these particles were confined to this much volume, but now they are confined to only half of the volume. So what is happening here? With increase in pressure, the number of particles per unit volume gets increased, and so what happens because of this? The particles will further enter into the solution. When there are more particles per unit volume, they will now be forced to enter into the solution. And when the particles go into the solution, what is happening to the solubility? The solubility increases. More particles going into the solution means the solubility is getting increased. So we can say that with increase in pressure, with increase in pressure, solubility of a gas in a solvent or a liquid is found to increase, or it increases. So with increase in pressure, the solubility of a gas in a liquid increases. If you are asked the reason, what reason will you give? It's because simple say that the number of particles per unit volume increases, and because of that the solubility of the gas in the liquid will also increase. This increase in solubility of a gas in a liquid was quantitatively first expressed by Henry, and it is given as the Henry's law. Let's see what is the Henry's law, what is the statement. Now as per the Henry's law, the solubility of a gas in a liquid is directly proportional. It is directly proportional to the partial pressure of the gas above the solution. So as per the Henry's law, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. Okay, and now if I take chi, what is chi? Mole fraction. If I consider chi or the mole fraction as a measure of solubility, okay, if chi is considered as a measure of the solubility, then the Henry's law can be stated in one more way. And what is that? It is the partial pressure of a gas in vapor phase, let's say it is P, is directly proportional to the mole fraction of the gas, which is chi, in the solution. Okay, I am considering mole fraction as a measure of the solubility of the gas. So the Henry's law states that the partial pressure of the gas in the vapor state is directly proportional to the mole fraction of the gas chi in the solution. Okay, let me show the same thing to you one more time. So our system was something like this. There is a gas here and there is a solution below that. The solution is what? The solution is this gas dissolved in a particular solvent. So let's say P is the pressure of the gas here above the solution, and chi represents the mole fraction of the gas inside this solution. Okay, so where is P? P is above the solution. It's the pressure of the gas above. And where is chi? Chi is the mole fraction of the same gas but inside the solution. So as per the Henry's law, P is directly proportional to chi. Okay, P is what? Pressure of the gas above the solution. Chi is what? Chi is mole fraction of the same gas, but it is in the solution. On replacing the proportionality, we put a constant And we get the statement of the Henry's law, expression of the Henry's law as P is equals to KH into chi. So P is equals to KH into chi is the mathematical expression for the Henry's law, where chi is called the Henry's law constant. And as you see that chi has no units. Chi is mole fraction. It has no units because it is the ratio of number of moles by number of moles only, no units. So KH should have units exactly same as that of pressure. And yes, Henry's law constant has units same as that of pressure. So Henry's law constant KH has units exactly same as that of pressure. So P is equals to KH into chi, mathematical expression for the Henry's law. So if we plot a curve taking pressure on the y-axis and mole fraction chi on the x-axis, the two are directly proportional, so we get a straight line from the origin, and the slope here gives us the value of the constant kh. Okay, so P is taken as y, chi is taken as x, and kh is the slope of this curve. One more thing about kh is that kh is, or you can say it depends on the gas taken. It keeps changing if you change the gas, right? So it depends on the nature of the gas which is being taken. And also it is observed that with increase in temperature, KH increases. With increase in temperature, KH increases, right? So look at the situation. P is equals to KH into chi. Okay, if it is so, let's keep the pressure constant. If the pressure is constant, okay, and you increase temperature, okay, you have increased the temperature, pressure is kept constant, temperature is being increased. What happens to KH? With increase in temperature, KH increases. So with increase in temperature, KH will increase. So KH is going to the higher side. Now because pressure is to be kept constant and it is a product of KH into chi. So when P is a constant and it is a product of these two, where one is increasing, the other should then decrease. So that means if you increase temperature, KH increases, or you can say chi will decrease. And what is chi? Chi is a measure of solubility. So with increase in temperature, we can infer from here that solubility should decrease. Okay, or the solubility decreases. So with increase in temperature, KH increases, and chi, which is a measure of the solubility of the gas in the liquid, is going to decrease. Let's now try to understand the effect of temperature. The effect of temperature on the solubility of a gas in a liquid. Okay, effect of temperature. Actually, the process of dissolution of a gas in a liquid is very similar to condensation. When a gas dissolves in a liquid, the process is very similar to condensation, and it is found to be exothermic in nature. Now, if you apply Le-Chatelier's principle, exothermic processes in which heat is released are favored at a low temperature and they are not favored at a high temperature, right? So if the dissolution of gas in liquid is exothermic, we can say that as per the Le-Chatelier's principle, with increase in temperature, solubility decreases. So this is simple, can be explained on the basis of the Le-Chatelier's principle. Now because the process of dissolution is exothermic, it will not be favored at a high temperature. So with increase in temperature, solubility will decrease. And this is the reason why the aquatic species, it can be the plants or the animals, the aquatic species are more abundant, they are more found, they are more abundant in cold water regions than hot water, than hot water. And you can understand they are more abundant, more common in cold water regions than in hot water, because when temperature is low, more gases going to be available, may it be carbon dioxide or oxygen. So when the temperature will be low, the solubility of gases is going to be more, and so more gases will be available when the water is cold rather than it is hot water. Now we will quickly take up a few applications of the Henry's law. The first application is that the soda water bottles are sealed, they are sealed under high pressure. The soda water bottles are sealed under high pressure in order to increase the solubility of carbon dioxide in water. Okay, so this is the first application. The second application is observed in case of scuba divers. Scuba divers, they dive in the deep sea, and what happens is the scuba divers, they suffer from a medical condition which is known as bends. They suffer from a medical condition which is known as bends. Bends is a highly painful condition, and it can be life threatening also. Now, what happens in bends? How is bends caused? It is caused due to the blockage of blood capillaries. It is caused by the blockage of blood capillaries by the bubbles of nitrogen gas. And this happens why? This happens due to increase in atmospheric pressure, due to increase in atmospheric pressure on going down in sea, and this further increases the solubility of gases in blood. Okay, so as the diver will go down in sea, the atmospheric pressure will increase, and because of this the solubility of gases in blood will also increase. So gases will start to flow through blood at a very fast speed. This will create bubbles of nitrogen gas, and that will block the blood capillaries. This is a painful condition which is known as bends. Now the important point here is to avoid this. Okay, to avoid this, the air tank which is carried by the scuba divers, the air tank is diluted. It is diluted with 11.7% of helium, and this is because helium has a very low solubility in blood. Helium has a very low solubility in blood. So some of the nitrogen is decreased, and in place of nitrogen around 11.7% of helium is added because of its low solubility in blood, to avoid bends to an extent. And one more last application that we will talk about is that those people who live at high altitude, you can consider the climbers also, and the people who live at higher altitudes in hill stations, they this again suffer from a medical condition. They suffer from a medical condition which is known as anoxia, and because of anoxia, they become weak. They become weak and are unable to think clearly. So climbers and people, those who live at hill stations or hilly areas, they suffer from anoxia, in which they become weak and they are unable to think clearly. Now this happens because of what? The reason is what? At high altitude, at high altitude, you know that the atmospheric pressure is low. And when the atmospheric pressure will be low, solubility of oxygen in blood is also going to be low. So there will be less oxygen available in blood. There will be less oxygen available in blood. If you compare it with sea level, there will be less oxygen available in blood at high altitude, and because of that lack of oxygen, the person will become weak and will be unable to think clearly. Conditions of the disease called as anoxia.